There we go. So instantaneous dipole. And the term instantaneous suggests that those electrons are only on one side of the atom for an instant. Okay, that's where that term is coming from. But it affects an overall sea of atoms. And what kinds of molecules do we see, or atoms do we see instantaneous? Do we see dispersion forces in? Remember? Everything. Everything. Why is that? Because everything has electrons. Yeah. So if something has an electron, those electrons can move. That movement can affect other atoms. And so everything that has an electron can have dispersion forces. So occurs, and we're just going to write everything in general here. Oh boy. This used to work better, I promise. Occurs in everything. Okay. Our next type of intermolecular force are dipole-dipole interactions. In order for molecules to experience dipole-dipole interactions, that molecule has to have a dipole. And the term dipole refers to a partial positive charge on one end of the molecule. If I do plus VE, that means positive. Okay? And then it has a partial negative, minus VE for negative, on the other side. So dipole, a molecule with a dipole has a partial positive charge on one end and a partial negative charge on the other. This is different than an instantaneous dipole because it exists it exists longer than an instant. It exists. Okay, so this figure shows an image of a liquid. Could be, for instance, HCl. Our hydrogen is going to have a positive charge. Chloride going to have a negative, partial negative, and so there's a dipole along that bond. And what happens then is that with the partial positive charge, that can line up and interact with a partial negative charge. And so we end up creating sort of a structure within a liquid, loosely defined structure. And there are defined interactions that tend to happen. Okay. We will look at a few examples of molecules that have dipole-dipole interactions. I think in some cases it can be really challenging to identify whether a molecule has dipole-dipole interactions. And so one of the things you can do is sort of look at specific types of bonds. The other thing that's really important, especially for smaller molecules, is remembering molecular geometries and electron geometries. Okay? So that goes back to, I don't remember what chapter that is in the textbook, but if you go back to thinking about geometries, how the trigonal, pyramidal, octahedral, tetrahedral, all of that. Okay, those are going to play an important role in deciding whether a molecule has dipole interactions. Questions so far? Yeah.
Dipole-dipole only happen in polar molecules?
Do dipole-dipole interactions only occur in polar molecules? Anyone want to answer? Yeah. Yes? Yeah. They tend to occur in molecules that are more polar. Now, let me say this. We're going to see an example. We could make an example of maybe a molecule. I'm going to draw a bunch of carbons here, all bonded together with hydrogens. And if I were to stop here, and if all those lines represented a carbon-hydrogen bond, that would be what? There's 5 of those, so that's pentane. You might not need to know. Might not know that now. That's totally fine. You don't need to. And this is a nonpolar molecule. It has carbon-hydrogen bonds but they're all sort of equally arranged around the carbon in tetrahedral fashion. And those carbon-hydrogen bonds pull equally from each other in a way that eliminates any dipoles. Okay? Now, if I add an OH, thank you. Now we've got a group on this molecule where we have two lone pairs of electrons on our oxygen. We've got a different geometry, and this sort of functional group is what we call that, will always have a dipole. But if we're comparing this molecule to something shorter, does anyone know what this is? With 2 carbons, ethanol, yes. So if we're comparing ethanol and pentanol, now we have a range of polarity. Okay, which one's more polar? Is that ethanol? Everyone agree? Yeah, so the length of the carbon chain, and we will talk about this in a little bit in more detail, the length of the carbon chain has an effect on the overall polarity of a molecule. So ethanol in this case is going to be more polar than pentanol. Okay. So there's there's a lot of considerations when it comes to intermolecular forces. That's part of the reason why I wanted to review it with you. So then we have hydrogen bonding. Okay. So hydrogen bonding only occurs with certain atoms that are bonded to hydrogen. Does anyone remember what those are? Yep. Nitrogen, oxygen. What's the last one? You're saying fluorine?
It's one of those. NOF, one of the 3 of those.
We agree, NOF? Okay. Actually, truly hard to hear. Okay. So if a molecule has a hydrogen bond, it is able to form hydrogen bonds. Okay, so how do hydrogen bonds work? This figure represents water molecules in a liquid form. Okay, and the oxygen atoms are in red. The white represent hydrogen. Those are bonded together with covalent bonds, hydrogen, oxygen, hydrogen. And then the 3 dots represent the hydrogen bond, and that's typical. You'll often see dotted lines representing hydrogen bonding. And so if you look at those interactions, those hydrogen bonds are always formed between a hydrogen on one molecule and an oxygen on the other, right? Yeah. Everyone agree? And so this forms sort of a structure, right, within water itself. And these hydrogen bonds are actually pretty strong, okay? In general, hydrogen bonding is stronger than dispersion forces, is stronger than dipole-dipole. But we're going to see some examples where there are some ways in which we can sort of exceed the strength of a hydrogen bond with other types of forces. So I guess what I'm trying to say about that is use this scaling sort of as a general trend, but not a rule. And then the last type of intermolecular, sorry, go.
Is it possible for like 2 hydrogen bonds to the same electronegative atom?
Is it possible for 2 hydrogen atoms to hydrogen bond to the same electronegative atom, for instance, in this case, oxygen? That's a really good question. For what you need to know, the answer is no. That's a question where I'm afraid to absolutely say absolutely not, because there might be some crazy instances in water, for instance, where you can have two hydrogens bonding to oxygen. We talk about the phases of water, right? We solid, liquid, gas. But there's actually like a dozen different phases of water, and some of those may have different types of interactions. Beyond the scope of this course. So in short, no. It's going to be 1-to-1. Okay, so then other questions, I guess I should pause. Yes?
So if a molecule has hydrogen bonding, would that molecule automatically have a higher boiling point than the dipole-dipole?
If a molecule has hydrogen bonding, would it automatically have a higher boiling point than something with only dipole-dipole interactions? It's a great question. How would we think about that? What are some other factors? Short answer is not necessarily. So what are other factors that play into the straight? Yes? Yeah, it depends on molar mass, right? So if you have a huge molecule, high molar mass, but only has dipole-dipole and cannot hydrogen bond, it may have a higher boiling point than something that can hydrogen bond. It's a great question. Yeah, good job. Anything else? Okay. So then ion-dipole interactions. These to me are sort of somewhat less interesting, but basically, if you have an ion, we have sodium and chloride here, represented in this figure, our chloride ion and our sodium ion, and they're dissolved in water. I guess solvation is kind of cool, actually, so we'll take a good look at this. So take a look at the way that the water molecules, that's what these are oriented around the chloride ion. And then compare that to the way the water molecules are oriented around the sodium ion. Let's take a look real quick. So one thing you probably notice is that the hydrogen atoms are oriented in the direction of the anion, the chloride. And that's because those hydrogen atoms have a partial positive charge. And then with the sodium ion, our positive charge, our cation, the partial negative charge of the oxygen atom in water is oriented towards that sodium atom. Okay? These ion dipole interactions change the orientation of the molecules if we're dissolving things. It's kind of interesting. Okay, so let's take a look at a plot. All right. Okay, so here we have a plot of our group 4 hydrides. Group 4. Oh, I'm so sorry about the writing. It's disappointing. I've left carbon off here for a reason, okay? So we have silicon hydride, germanium hydride, and tin hydride. We're plotting boiling point on our y-axis and number of electrons on x. Okay? Why are we thinking about boiling point? How do boiling point and intermolecular forces relate? Yeah, so greater intermolecular forces, the higher the boiling point. So if we have high intermolecular forces, we'll have a higher boiling point. So up, higher IMFs, higher boiling point. So we could put intermolecular forces on y-axis and then take off the numbers, but this is data, so data is easier to think about. We also have number of electrons on x. What else could we use instead of that? If we wanted to use something that would follow the same trend, but not electrons. Let me let someone else. Yeah.
Molecular weight.
Yeah, we could do molecular weight. It's going to follow the same trend. As we increase molecular weight, the number of electrons increases. Okay. And so we know that as we follow the periodic table going down a group, the mass increases, number of electrons increases. And so if we're comparing all the hydrides, we'll see that as we increase the molar mass, or we increase the number of electrons, the boiling point increases. And so our tin hydride has a greater boiling point than the silicon hydride. Same way as to say the tin hydride has a greater number of intermolecular forces than the silicon hydride. Which intermolecular forces are present in the complex? Dispersion. Yeah. Anything else? Yeah. You think dipole-dipole? Anyone agree? Why not? Why is it nonpolar? Okay, so we need to look at the structure in order to figure out if this is polar, right? So we have, if we're going to draw a Lewis structure, for our silicon we're going to have 4 electron contributions, and for each hydrogen we have 1, so we have a total of 8. And so if we need to arrange 8 electrons around the silicon, we're going to do bonds first. And so we have 1, 2, 3, 4, 5, 6, 7, 8 for our geometry, or for our orientation of atoms around the center atom. What molecular geometry is that? Tetrahedral, right. And so tetrahedral is kind of hard to imagine, but each of the pools from the hydrogen away from the silicon in terms of electrons, or it's actually going the other way, it doesn't matter. They're all equivalent, okay? So a tetrahedral geometry, if all of the atoms arranged around the central atom are the same, you're not going to see any dipole-dipole interactions. Okay? Because the pool around the central atom is equal in all directions. That one I think is really hard to picture, because the tetrahedral is a funky shape. It's not something we're used to. I wish I had brought a model, but I didn't think of it ahead of time. Okay, so we only have, that's a long way of saying we only have dispersion forces in these molecules, in these hydrides. Does that make sense? Okay. Yeah. Well, here's the question, and then I answered it for you. Okay, so what intermolecular forces give rise to the observed trend? We only have dispersion forces. And how does the strength of the intermolecular forces in liquid germanium hydride compare to those in the silicon? They're greater. I really apologize about this writing. My handwriting really is not at all like that. That's bad. Okay. Cool. So now let's make a prediction. Where do you expect the boiling points for the group 5 hydrides to be relative to the group 4 hydrides? It could be the same because they have the same number of electrons. It could be lower, is it because the dispersion forces decrease across a row? Or higher because the group 5 hydrides have a greater dipole-dipole forces. Yeah. Higher temperatures. People agree? Getting lots of nods? Yeah. So they are higher. So we're looking at pH 3, for instance. If you draw the Lewis structure of pH 3, you're going to end up with a central phosphorus atom, which is going to have a contribution of 5 electrons. You're going to have 3 electrons from the hydrogens, total of 8. We need to toss our hydrogen atoms in the mix here, form some bonds with the phosphorus. So now we've accounted for 1, 2, 3, 4, 5, 6 electrons. We have 2 extra, we need to add on a lone pair. So what geometry does this get us to? Yeah, trigonal pyramidal. So hard to say. Trig, pyram. We've got a lone pair of electrons. Okay. We've got that lone pair. Now we're going to have some dipole-dipole interactions. Okay. Questions on that? Yeah.
There's electron geometry, or what? There's 2 different ones, right?
Yeah.
What are they called? Molecular.
Yeah, so I always call it electron geometry, but my TAs were doing a practice problem and they used a different term, which might mean it's different in your textbook. But I always call it electron geometry, which includes the lone pairs, and then it's the molecular geometry where you ignore those.
Molecular would have been tetrahedral, but
It's not tetrahedral, it's still trigonal pyramidal. Because you have to account for the displacement of the hydrogen bonds because of the extra space the lone pair needs. Yeah. Okay, we're gonna skip that. So one way to think about these molecules, and something you may want to sort of make a habit of looking up if you feel like it, I don't know, it's kind of useful, are electrostatic potential maps. What these do is they show you the arrangement and the density of electrons around a molecule. And the colors represent different densities. So the red represents a higher negative density charge, so more electrons, and the positive, sort of lower density, is blue. And then green, this green representation here in methane, says basically that the electrons are distributed evenly across that molecule. So again, methane has tetrahedral geometry. Ammonia has trigonal pyramidal. And so those different geometries, there's a lone pair of electrons on that nitrogen. It's going to look something like this. Lone pair, lone pair. Okay. These can be really useful when you're thinking about or asking yourself if a dipole is present in molecules or looking at the structure. Okay, so finally to answer officially with data, the question of where the group 5 hydrides lie relative to the group 4. Yes, they do have greater boiling points than the corresponding group 4 hydrides. You see the displacement vertically in terms of number of electrons. Okay. Now let's add in our ammonia and our methane, which we just saw the electrostatic potential maps for, right? We know that ammonia has that lone pair of electrons. It's able to have what kind of interactions? 2 of them. Dispersion. And what else? Dipole-dipole. That says dipole-dipole, I promise. What about tetrahedral? What about methane? What does it have? Just dispersion, right? Okay. So why though? I said something wrong, didn't I? Who wants to correct me? How many types of intermolecular forces are in ammonia? 3. What did I miss? Yeah. Hydrogen bonding. So we have an NH group, which is what I was going to ask, is why is ammonia so much higher in terms of boiling point than the methane molecule or the pH 3. And that's because not only does it have dipole-dipole and dispersion, like everything else on the board, but now it has hydrogen bonding, so it makes it special. Okay. We're going to draw a line here. So the ammonia boiling point is somewhere around 240 Kelvin. Okay. Our antimony hydride has a boiling point above that. Okay. Maybe almost 260 Kelvin. Okay. And this goes back to your question about if something has hydrogen bonding, does it automatically have a greater boiling point than something that doesn't? And this is a great example that shows that no, that's not always the case. So the dispersion forces in dipole-dipole interactions, most of the dispersion in this case, are giving rise to a much higher boiling point, a higher boiling point in the antimony hydride compared to the ammonia. Okay. Questions? Yes?
Are van der Waals forces the same
Ah.
as dispersion?
Yes, van der Waals are the same as dispersion. Yes, I knew there was another term that I was forgetting. Dispersion, London dispersion, van der Waals, those are the same. Yes. Good question. Yeah. Yeah, so the question is it because of the size of the antimony hydride that makes it have a greater boiling point than ammonia? And yes, so it has greater electrons, greater molar mass, greater amount total of dispersion forces, which makes it have a higher boiling point. Cool. Yeah.
So how would you know when the molar mass is not just big enough that it would override?
Yeah. How do you know when you get to a high enough molar mass that it's going to overcome, in terms of make it have a greater boiling point than something that has hydrogen bonding? Look it up. That's actually a great answer. Yeah, there's no good rule for that. And so usually if we're going to ask you a question of that type, they're going to be comparable. All other factors are going to be held constant. Yeah. Yeah, so if you were to say, would I ever ask on an exam, what has a higher boiling point, antimony hydride or ammonia? That's something you would just have to memorize. So that's not really testing anything useful. Where are we at? Okay. Sorry, can't decide where I want that. Okay, so why is the boiling point of H2S lower than the boiling point of H2SE? So the sulfur hydride versus the selenium hydride. Yeah, okay. Anyone? I was making sure I read over the. So we have fewer electrons and weaker dispersion forces in H2S, correct? That's true. The structures of these are going to be the same, and they're going to be the same as water. Okay. Again, we talked about water. It can hydrogen bond. So why do you think the boiling point of water is so much higher than that of ammonia? Hydrogen bonding, but both can hydrogen bond. Yeah.
Oxygen is a lot more electronegative, and that's times 2 hydrogens.
You have more electronegative oxygen atom times 2. I think we're getting on something here with the hydrogen atoms. Yeah.
You have more open areas of bond for hydrogen bond to or oxygen.
Yeah, so more open areas for the hydrogen to sort of approach the oxygen. So let's draw an oxygen molecule. Yeah, no, you all are on the right track. This is kind of a fun thing here. So we have two lone pairs on our oxygen. So now, where did I think you asked, can you have more than one hydrogen bond? If you have one lone pair, you can have one hydrogen bond, right? If you have two lone pairs, now we can have two hydrogen bonds. All right? And so if we had 3 molecules of ammonia, and we looked at their interactions, here's our 3 molecules of water, we can see that all of those are hydrogen bonded together, right? If we have 3 molecules of ammonia, we can have one, whoops, H, that's an H, that can hydrogen bond, and another one. But we end up eventually running out of sites where you can actually get greater numbers of hydrogen bonds for the same number of molecules of water as you can for ammonia. And so you can get a tighter network of hydrogen bonding, which gives rise to the greater boiling point. This is also the reason, well, I'll go over there. Strike that. Okay. I kind of zoomed there, didn't I?
So, you know how, like, on the bottom, you have, like, the regular bonds for, it's, like, H, bonded to oxygen, and then you wrote, like, the hydrogen bond on the top of the molecule?
Uh-huh.
So, with the H at the, like, the 2 H's at the bottom of the oxygen, would those also consider hydrogen bonds? Or no?
These, okay, so that's a good question. So if the hydrogen is directly bonded to the oxygen, that is not a hydrogen bond, that's a covalent bond with a hydrogen. Yeah. The only ones, so the HOH, these bonds are covalent. And anything else where we draw a dotted line, that's going to be the hydrogen bond. And yeah, it's kind of like if you think about what that means in terms of real life, what it really looks like in solution, I'm sure no one can actually answer that. But there are weaker interactions between individual molecules of water compared to the atoms that are bonded together within that molecule. Yeah. Ooh, ran into that. Yeah, so if you think about boiling, right? So we boil water, we create steam. We're generating individual molecules of water by doing that. But we aren't breaking any oxygen-hydrogen covalent bonds. We're only breaking hydrogen bonds. Let's see what my next slide is here. Where did it? That question was kind of boring other than the water thing. Let's see. Undo. Why is the boiling point of H2S? That's this one. Higher than that of SiH4. That's this one. Take a look at the question. Come up with an answer. Sure. Okay, so boiling point of H2S higher than SiH4. Yeah, what reasons here? Yeah. D. So, because H2S is polar and has dipole-dipole forces. Yes, that's correct. So the silicon hydride is tetrahedral, does not have any Dipole-Dipole Interactions, no lone pairs. It's a nonpolar molecule. H2S is polar. It has dipoles, can have dipole-dipole interactions. This works on Zoom. It works, but do you guys like doing clicker type questions, or what's it called? Top hat? Do you like those? Sorry to the two people who just nodded emphatically. Good question, I guess. I'm glad I asked. All right, let's finish up here. Okay, so I think this is our last questions. So why is the boiling point of H2S, which is circled, lower than the boiling point of water? Easy one, right? This guy knows. He raised his hand. Who else? Yeah. Hydrogen bonding. Thank you. H bonding. Okay. Let me just get last question. We have two more now. Let's go to this one. We talked about tetrahedral molecules. This is a representation of a tetrahedral molecule. This is dichloromethane. Dichloromethane. Okay. What types of intermolecular forces do you expect in this molecule? Dispersion, easy one. Good work. What else? Definitely dispersion. That's a check mark. And B, which is dipole-dipole. Everyone agree with that? Yeah. So now we have different bonds to the central carbon atom. We have a couple carbon hydrogen, we have a couple carbon chloride bonds. Those do make a dipole. There's not equal pull around the central carbon atom anymore. So we have the dipole, now we have dipole-dipole interactions. No hydrogen bonding. Okay? Yeah? No, you're good. Yes.
So that means that, and carbon has 4, so
Yeah.
if all of them are bonded with one of the valence electrons, right? And sharing those, then why is that considered dipole-dipole? It's all like they're all sharing. Does that make sense?
I think, yeah. Okay, so I think what if we draw the Lewis structure, maybe this will help. So we have 7 from chlorine, which is a total of 14, plus 2 electrons from the hydrogen, so we have a total of 16. We've drawn 4 bonds, so that's 8 electrons, right? Wait, did I do math wrong? Oh, no. No, yeah, I did do, something is wrong. What am I doing wrong, people? 1, 2, 3, 4, 5, 6, 7, 8. We need to draw lone pairs around here, and it should look like this. So when you have the lone pairs around the chlorine, I think that might be what you're missing. They don't go on the central carbon atom. So carbon can only have 4 bonds, or very rarely does it have lone pairs. Uh-huh. Is there still a charge on chlorine? Yes. Oh, okay. Hold on, guys. Don't leave yet. Don't get excited. This is a good question. So, yeah, chlorine is more electronegative. So it is going to be drawing electron density in that direction to a greater extent than the hydrogen. That's why there's dipole-dipole. And if you're wondering about this question, this is a great example. If you pull up the electrostatic potential maps, you can look at methane versus chloroform, dichloromethane, and then the one with 1 chlorine. Okay, no. It's escaping me while I'm trying to rush. And it has a great example of that. Real quick, don't leave yet. We've got 3 minutes. Take a look at this table, okay? So these are different types of molecules and they're general types of intermolecular forces, okay? It's really good to become familiar with these. They're formulas and they're sort of functional groups as we call them, okay? These are really going to help you when you're thinking about whether a molecule is polar or not, right? Now, do we want to do a demo? Yeah. Okay, let's do a demo. So we're going to look at whether 2 liquids are miscible or immiscible. What does miscible mean? They mix. What's immiscible? They don't mix. Here we have ethanol and water. And here we have hexane and water. What forces do we have in ethanol? See, hydrogen bonding. Dipole-dipole, dispersion. And we have water with all 3 of those, right? So are they miscible? Yes? No? We're following the light dissolves light rule. So if we have similar intermolecular forces, they should mix. So this is the ethanol, the water is dyed blue with the food coloring. Mix it up. We'll wait a minute. They're not going to separate. Okay. Now we have, and you know that, right? Now we have hexane. It's our colorless solution, and water dyed blue again. Hexane, very similar to pentane. I'm not going to draw all of the hydrogens, but each one of those lines represents a hydrogen. What type of forces do we have there? London. That's it, right? Are these going to mix? No.